For a long time, physicists believed neutrinos had no mass. Then they discovered they do have mass. But now, some recent findings suggest this mass might actually be negative. Sounds crazy? Let me walk you through one of the most debated scientific findings of this year. Neutrinos are known as ghost particles. They are the second most abundant particle in the universe, and they barely interact with anything. Trillions pass through your body every second, and you don't even feel them. But here's the twist. Despite being so elusive, neutrinos leave a mark on the cosmos. As they zip through space, they gently smooth out the tiny ripples in matter, ripples that would otherwise grow into galaxies. That tiny smoothing, we can measure it. In doing so, neutrinos create a stunning bridge between the smallest particles and the largest structures from our universe. Through particle physics experiments, physicists realized that neutrinos oscillate. That is, they change flavor as they travel, proving that they must have a different mass, and a total of 3 flavor states: electron, muon, and tau. As a consequence, there are 2 types of mass ordering of neutrinos. One is the so-called normal hierarchy, where the 3 neutrino types are ordered from lightest to heaviest. In this case, 2 neutrinos are relatively light, and the third one is significantly heavier. The other is inverted hierarchy, where the 2 heaviest neutrinos are nearly equal in mass, and the lightest one is much lighter. Using results from neutrino oscillation experiments, and assuming that the lightest mass of the neutrinos corresponds to 0, we can estimate a lower bound for the total mass of the neutrinos from particle physics. Direct searches, like the KATRIN experiment, the most sensitive instrument to measure neutrino mass to date, study the beta decay of tritium. So far, they have placed an upper bound of about 0.45 eV on the mass of the lightest neutrino. That translates to a total mass of 1.35 eV. So we're left with a big gap, a wide window between the minimum mass we know must exist and the maximum mass. And this is where cosmology comes in. Cosmology offers a powerful and complementary path to study neutrino masses. The early universe produced a vast number of these tiny particles, which have been traveling for billions of years, influencing the background evolution of the universe. If the total mass of neutrinos has remained constant over time, as current estimates suggest, we can trace their influence by comparing different epochs of the universe. In practice, this means combining observations of the cosmic microwave background with the large-scale distribution of galaxies we see today. To make this comparison, cosmologists rely on a well-established theoretical framework known as the lambda-Koldach-Matter model, which describes the evolution of the universe. Neutrinos' large thermal velocities prevent matter from clustering, leaving a subtle but detectable imprint in cosmological observables. By combining early and late measurements, cosmologists have placed some of the tightest constraints on neutrino masses to date. Recent cosmological analysis, drawing on data from the Dark Energy Spectroscopic Instrument, the South Pole Telescope, the Atacama Cosmology Telescope, and the Planck Telescope, have pushed the limits on the mass of neutrinos to astonishing levels. They now report an upper bound as low as 0.048 electron volts. At that level, the normal mass hierarchy is disfavored at 98% confidence, and furthermore, the inverted mass hierarchy at 99.9%. These are some of the tightest constraints we have ever seen, an order of magnitude stronger than those from direct laboratory experiments like KATRIN. But there's a catch. These cosmological limits are indirect. They're not measured in a lab, and they're inferred from how well our model of the universe fits the data. And if any part of our model is wrong, whether it's the underlying physics, hidden systematics, or subtle effects in the data, then the neutrino mass estimates could be skewed towards negative masses. Much of this arises because of tensions between measurements from the early and late universe, like differing estimates of matter abundance, which can significantly shift the neutrino mass limits. These constraints usually assume neutrino masses are positive, but removing that prior sometimes hints at negative values under the standard ΛCDM model. However, we must be clear, neutrino masses are physically positive. Meanwhile, recent DESI results, combined with other data, challenge ΛCDM itself, suggesting the universe's expansion may be dynamic rather than constant. In such dynamical models, the upper bounds on neutrino mass relax, reconciling cosmological results with those from particle physics. It's an exciting path, but one that remains largely uncharted. As we look deeper into the universe, we're not only chasing neutrino masses, we're challenging the very foundations of cosmology. With upcoming experiments like the Ried Observatory, we'll face new challenges in controlling systematics while pushing statistical methods to their limits. And along the way, the neutrino results might just hint that the cosmological model we rely on needs to change.